Welcome back to the Formulaic Approach channel. Now in this video, we are going to be dissecting the progressive wave equation. Now I already have a video where I derived the equation for you, but someone reached out to me last night that there is something that is confusing about the forms of the equation. So today I'm just going to be majoring on the forms of the equation, even though I might still have to do a little bit of derivation at the end, but I want to first explain the forms of the equation and why the equation is the way it is. In fact, that's what I'm going to delve into, okay? But let me first explain what you asked for, okay? Now, you see, first, you have to understand that a wave is defined in terms of time and space, okay? A wave is defined, we say it is tempospatial, okay? A wave is defined tempospatially. Now, what does this mean? It means that a wave is defined in terms of time. The word tempo refers to time, and spatial refers to what? Space. Okay? So simply put, a progressive wave is just harmonic oscillation of a particle plus some, phase difference. Okay? Phase difference between different oscillating particles. That's a wave. Now, a wave is not seen as just one particle, okay? And that's what some students might not even understand, okay? Now, there are two forms of the equation. Which are y equals a sine of a sine theta minus phi. Okay, you must have seen this before. Y, and the second form is a sine of phi minus theta, or this could be what you saw, that a sine, now theta in that case is omega t, all right, then minus, I've derived this before, okay, so at the end of this video I might have to show you that again, but I'm just trying to show you the different forms you might see in your textbook. Then this guy will be kx, keeping in mind that k is constant, 2 pi over lambda. This is the phase that is defined by space, and this one is the phase that is defined by time. Okay, all right, so this could also be written as a sine of kx minus omega t. So these are the two forms that might be confusing us, yeah? All right, so keeping in mind that this can be transformed into a sine of 2 pi ft. I'm trying to write all the possible forms that it might appear in your textbook, okay? Or a sine of 2 pi x over lambda minus minus 2 pi ft, with this corresponding to this and this corresponding to this. All right, now what I want to basically explain is why we have these two different forms for the same equation in different textbooks. Now, number one thing I want you to know is that it is based on the convention that is adopted by the author of your textbook, okay? But they are practically defining the same thing. Now, listen to me first. I want you to take your calculator now your scientific calculator, okay? And type in sine. I want you to know first that sine of theta, okay? I want you to type in sine of theta and type in, let's use a specific angle actually. Let's use a specific angle, like sine 30. Type in sine 30, okay? And type in sine of minus 30. Then type in sine minus sine 30. Okay, and type in, yes, that's it. Now, what will sine 30 give you? It's going to give you 0.5. What will sine of minus 30 give you? That will give you minus 0.5, because in trig function, you know that sine of minus theta is just equal to the negative of sine of theta. So it means that negative of sine of theta is going to what? Minus 0.5, which means what? They are the same. Okay? So either way I write it, I'm still going to have minus 0.5. I hope that is clear to you. The sine of the negative of an angle is equal to the negative of the sine of that angle. Does that make sense? All right. So what I'm saying in essence here is, now consider these two forms. Let's take this form as the form. This is the form that I like to use, okay? Which is the form I used in proving my equation there. Omega t minus kx. You believe with me that is the same as negative of omega t, negative of kx minus omega t. Do you believe this with me? Okay, let's check that out. Let's check that out. We're going to have minus kx plus omega t. And you're going to see that if I rearrange this, it's going to become omega t minus kx. Does that make sense now? All right. Now this is the same as this, right? Okay, now I want to show you how that this thing checks out, okay? This thing checks out. Now, you see, one first thing I want you to know is that the wave equation is described, we compare it to the motion of a circular motion, okay? The circular motion of a particle. The only difference here is that in circular motion, we are describing just one particle that is moving in a circular path. But for wave, we are describing many particles, okay? Many particles that are oscillating. Now, we are talking now with respect to one circle, okay? One circle, all right? So let me quickly show you why this is so. Let me show you why this is so. So what this means is that if I am saying that my y1 is equal to a sine of omega t minus kx, and I put y2, let me put y2 to be a sine of kx minus omega t. I am saying that that both expressions are the same. They are saying the same thing, okay, but in different ways. So what I am saying in essence with this proving I just showed you is that y1 is going to be what? A sine omega t, the same thing, minus kx. And listen now, the y2, now what? The y2 is going to be a sine of negative omega t minus kx. Does this make sense to you? Negative, because by the time I turn these in the other direction, what am I going to have? I'm going to have kx minus omega t. Does that make sense? This opens the bracket and I will get this, right? So this is still y2. I've not changed anything. Only that I inserted my minus, right? So this is still, so negative of the angle I have here that this produces, okay, is going to be, the negative of this angle is going to be my y2. Okay, so what do we now mean by y1 and y2? Why are they different? What is this minus sign for? Given that, okay, so if I bring this minus out from here, from what I proved to you here, that the sign of negative theta is the same as negative sign of theta. If this is true, then you agree with me that y2 can be rewritten as minus a sine of omega t minus kx. Does this make sense? So what this means is that I have brought this one to become what? Negative. I have made this one what? Negative. Remember that this entire place here is y1, right? A sine omega t minus kx in it. Then this minus here means that y2 is the same as what? Negative y1. What that means is that if I were considering my oscillation on the y-axis now, but considering the y component, since I'm considering the y component of my oscillation, now this y2 is going to be, if y1 were positive here, y2 is going to be just the opposite, in the opposite direction. Okay, remember amplitude is seen in both positive axis and negative axis here. Yeah. So this y2 is going to be the negative of y1, such that if y1, I pick here as y1, then the negative, the other side of y that has the same magnitude but the opposite direction. Okay, and you see the direction is really not doesn't really affect much here. Do you know why? Because if I turned my graph here, I'm going to have the same value. Okay, I just switched. It's called a phase shift. All right. It's called what? A phase shift. Okay, now let me show you another thing mathematically. If I have sine of minus theta is the same as the sine of theta plus pi. You can type that in your calculator using the fact that, using angle 30 that we used, sine of negative 30 is the same as sine of 30 plus 180. Sine 30 plus 180 is going to give you, sine 30 is minus, sine minus 30 is minus 0.5, right? So this will also give you minus 0.5. You can use your calculator to verify that, all right? So since this is the case, so I am just showing you that what we have done here is just a phase shift, all right? So now let me go back to the beginning of derivation here, so that you will now understand why there is a, why we are talking about phase shift. Okay, it's not really different. Okay, it's not necessarily different. It's just talking about the oscillation in the other direction. The oscillation happening in the opposite direction, which is pretty much the same if you understood what I already said in the circular motion. But let's say you don't even understand. I'm going to start from the beginning again. So to show you that, to show you first why we even have to subtract or add, okay? Because if you don't understand that they are the same, you probably don't even understand that. You probably don't even understand why we are subtracting here. So if I were to put plus here now, you might even be confused that is minus. I normally see in my textbook. Now this man has brought addition again, and you see they are actually both correct. They are both correct. These two forms are correct. If I put an addition there, it's still correct. All right. Now let me show you what. 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 Everybody, let me show you what. Let me show you. Come on, let me show you what. Let me show you what. All right, so now I already told you that wave is defined tempospatially, yeah? So it means that to a wave equation, there is what? To a particular wave, all right? I told you that it's just simple harmonic, right? Harmonic oscillation. And in addition to a phase difference between two particles that are at different position, two or more particles at different position. Okay. Now let's first understand for a particle that is moving in a circular path. Now, for a particle moving in a circular path like this, if I wanted to define the vertical displacement from the point to which the oscillation is set, or from the x-axis, from the space, okay? All right. What I'm going to do is that I'm going to set my x-axis like this, and I'm going to set my y-axis like this, okay? So that if, as my wave is moving in one circle, so this thing now, this baba now is moving like this in one circle, yeah? So at a particular point in time, it's going to be around here, yeah? Okay? And as that time is increasing, what's going to happen? It's going to keep, increasing in its angle. Does that make sense? As the time increases, I said it's defined in terms of both time and space, yeah? All right, so as I'm swelling, as I'm, as that thing is engaging in circular motion, for its one circle, at a particular time, it will be around, let's say it started from here, it will be around here. At a particular time, it will go 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 here, right? Okay, so as the time is increasing, the angle that is having is increasing, yeah? Like this, at a particular time to go here, at a particular time to get here, until it makes a circle, right? Okay, now let me go back by itself. For those of us that don't understand how a wave motion is similar to a circular motion of a particle in a circular path. All right, now look at my hand, for example. So if I am going like this, watch me. Now my hand is going like this. This marker on my hand is going in this direction, okay? It's going this way. Now let me do something. I'm going to change my direction, my frame of reference. How did this here? I'm going to change from this direction now to, I'm going to turn to this now. Now watch. It's still circle, okay? I've only turned from here. My hand has stopped facing, is now facing this direction. So I'm still going, I was going in a circle like this, yeah? Now I've turned and turned and turned. Now I'm going like this. Now, actually, if you were seeing in two dimensions, the reason why it might not be so obvious now is because we actually see in three dimensions. Now, if you were seeing in two dimensions, the only thing you'll be seeing is an upward and downward displacement. Does that make sense? Do you agree with me that this circular path that this hand is still engaging in, circular path motion that this guy is still engaging in 2 dimensions can only be represented in what? In both upward and downward direction, provided I am drawing on a single plane. Does that make sense? So it's just up and down you're going to see. It's just up and down. Okay, if that makes sense to you then what's what I'm going to do? Now as I'm going up and down and up and down and up and down, provided I'm in a straight path, but going up and down, the moment I displace space now, you know time and space here, so I now displace my space like this. Once I displace, what do I have? I have a wave. Does that make sense? I have a wave. Alright. So just stick with me. You are going to understand why we have different forms of the equation, why we can even put addition in the equation and all of that. Depending on the textbook you have seen it from. Okay, seen it in rather. Right now, look at what I'm going to do now. So at a particular point in time, so we are now talking about just one particle now. At a particular point in time, that particle is going to be here. Alright, so if I want to discuss or describe the vertical displacement away from this my x-axis, we're going to call here y, okay, and this is going to be my angle theta. Okay, so how do I describe this place? I know that from here to here is the amplitude of my wave, right? That is, my wave cannot go, the particle cannot go away or shorter than this radius. Does that make sense? So the radius of my particle oscillating, of the path of its oscillation, is going to be the amplitude. Does that make sense? You know the amplitude is defined as the maximum upward or downward displacement. Yeah. All right. So this guy cannot go more than that, and it cannot go less than that. So this is going to be my amplitude. Does that make sense? All right. So relative to what I have here, I can define my vertical displacement. Since I have here hypotenuse and I have here being my opposite. Now, which trig function relates my hypotenuse and opposite? That's sine, yeah? So sine of theta is going to be what? Opposite, which is y, over adjacent. Hypotenuse, which is what? My amplitude, okay? A is amplitude, A is amplitude. Alright, so over 1, by the time I cross multiply, I'm going to have y equal to a sine of theta. Does this make sense? Now, this guy, now why can we not simply define our wave like this? That this should be it. That will now say y then is equal to a sine of omega t. Now, if you have seen my video on circular motion, this is where we stopped, right? We needed not subtract a phase difference, yeah? Now, the reason why we cannot stop like this is that a wave is not seen, if you describe our wave like this, if we describe a wave like this, or a motion like this, this is the motion of a single particle oscillator, just one oscillation, one oscillator. This is the way we describe it. But a wave is, a progressive wave is, is stretched, right? A wave that is continuous, yeah? Do you understand? Progressive wave, continuous, yeah? So, a progressive wave is not seen as one oscillator. It's seen as many particles oscillating with at different time interval and space, depending on your reference point. Does that make sense to you? Okay? So, I said that a wave is what? A simple harmonic oscillation in time, okay? Plus an additional phase difference between many particles. That's how to view it, okay? View it as many particles that are oscillating, but those particles are not, they are out of step or out of phase. The real term we use is out of phase, okay? Those many particles are oscillating, but they are out of phase. Does that make sense? Or out of step. They are not in the same path. Do you understand now? So when we now describe the motion of a wave, here's what we now do. We now introduce our phase difference that will occur between both waves. You are going to understand. Just listen. Calm down. Now if I have y equal to a sine of omega t. If I stopped here, I have described only one oscillator. Okay? But we are describing a wave, and I said view it as many particles because it's a progressive wave, yeah? And those particles are out of phase by each other. They are not at the same point. Meaning that if I have a wave being at a crest at a particular point, x equals 0, at my origin here. And my wave, wave is defined in time and space, right? So this will be my time x rather, x-axis. This is my time, this will be my space. Okay, so at a particular time t, my wave at point x equals 0 is, one of my particles is at the crest. Another particle that is on the same point cannot be at the crest. It's going to be at the trough in the other direction. Do you understand that now? It's going to be at the trough in the other direction. What that means is that our particle is going to either lag behind, in this case, is going to be lagging behind this, my particle. The particle that is on the other side of this, my wave. So for example, I create a wave that looks like this. So at a particular point in time now, at a particular point here, where my x equals 0, if I describe this, my particle that is at this point as being at this point crest, another particle that is oscillating at that same point is not going to be at crest. It's going to be at its own what? At its trough. Does that make sense now? So it means that both of these particles are what? They are lagging each other. Okay? So one is leading, the other is lagging. And as you can see, my guy here is leading. Does that make sense? So that is why we have to either add or subtract a phase difference. Now you might say, where did I bring this one from again? Add or subtract. Now listen. If the wave I am talking about, the horizontal displacement, the vertical displacement of the wave I'm talking about is leading, for example, let's say this is particle 1, particle 2. In this case, you can see already, let's say particle A and particle B. You can see already that particle A is leading particle B. Does that make sense? Yes. Is leading particle B. Okay, so since it's leading particle B, then it's going to be leading by how many degrees? 180 degrees. Does that make sense? So that is why we can say that y is equal to what? A sine omega t plus phi. Does that make sense? And why we usually use x, why we usually use minus rather, is that we always define a wave that is already leading. Okay? We always define a wave that is already what? Leading. So that our point of reference, usually the starting point, for example, is lagging, any particle at that point is lagging the position of our wave by a particular amount of phase difference. So we now put subtraction. Does that make sense to you now? So another way to view it is this. Now, a wave that is traveling in the positive x-axis, okay? A wave that is traveling in the positive x-axis is going to be leading our reference point. So this is where we define it. Does that make sense to you? Does that make sense to you? A wave that is leading. Yes, a wave that is in positive x-axis, moving in the positive x-axis. This is the way we define it because our reference point is the starting point in this case. And a wave that is in the negative x-axis is going to be defined like this. Like this. Why? Because in that case, our x, remember that pi is equal to what? 2 pi is equal to kx. And k is what? 2 pi over lambda. So it becomes 2 pi x over lambda. But remember that x is now negative here. So it becomes negative. Negative times negative becomes what? Positive. So that's why we put negative here. Okay, so that the negative will cancel out if our wave were to be leading. Okay? Our reference point is leading. So if our reference point is still the starting point, if our wave were to be moving in this direction, what that means is that our reference point is leading our wave. Does that make sense? Our reference point is what? Leading the wave. So because of that, we're going to have this formula. I hope that is clear. Okay? Now, if that is clear, then you will now understand it when I say that our wave, so this wave now becomes y equal to a sine omega t minus kx is the same as, now, so this one, so if this were for, this is for negative, positive x-axis, which is this thing I drew here, this is positive x, this negative x. Okay, so my wave is in this axis. If I turn this motion by 180 degrees, see, this is just turning 180 degrees from here like this. I turn to this direction. The same theta is theta, yes, huh? So I turn by 180 degrees. What will you see? What you basically see is a wave that has shifted to the negative y direction. So what you will see is what? Minus y in this case. And what does minus y mean? Minus y now means minus a sine of omega t minus kx. Does that make sense? And that means that it's still the same as a sine of minus omega t minus kx. By the time I do this, why? You now have proven that here. Okay? So a sine of, by the time I open the bracket, I have kx minus omega t. Did you see that my equation are turned around now? So it depends on the convention and the phase we are considering. Okay, all right. I hope I've been able to do justice to that. Now let me quickly do a little bit of proving now. The proving I talked about. So by the time we introduce our wave, our phase difference here, now we're going to have minus phi, so that y can also be set to be a sine of omega t minus phi being 2 pi x over lambda. Now for those of us that might not understand that omega t is actually equal to theta. Why? Because omega is angular speed. If you remember in circular motion, so angular speed is angle covered per time, right? Angular speed is angle covered per time, just like speed equals distance per time. Yeah. Okay. So that's where this is coming from. And remember also that omega is what? 2 pi over 2 pi f. And how did I come about that? You know that if the thing, the motion, the circular guy, covered, if the theta is equal to 360, remember that 360 is the same as what? 2 pi, yeah? Okay? If the motion is a complete circle, then we have 2 pi over t. Recall also that f is equal to 1 over t, which means that t is equal to what? 1 over f. Does that make sense? So, in that case, 1 over t, which is what we have here, 1 over t is the same as f. Right? Since 1 over t is the same as f, you know that omega is 2 pi times 1 over t, yeah? So this is f. So omega is equal to what? 2 pi f. Does that make sense? Therefore, y can be redefined as a sine 2 pi f dot t minus 2 pi x over lambda. Does that make sense? Then our wave can be rewritten as y equals, now these are all the forms of the equation that you can use to solve questions. Alright, so let me introduce phi here, so that here will be kx, alright? So that y equal to a sine, 2 pi is common, yeah? 2 pi is common between ft and minus x over lambda, okay? I could also decide, you know that v is equal to f lambda, yeah? Since f is equal to v over lambda, so v is equal to f lambda. Alright, so f will be equal to v over lambda. Therefore, I can say that y is equal to what? Let me bring the z here. That y is equal to a sine of 2 pi f, which is now what? V over lambda t minus x over lambda. Okay, so this can turn to 1 over lambda is common. So y equal to what? A sine of 2 pi over lambda into bracket dt minus x. So these are the different forms of the equation that you can work with. I hope this is very, very clear. This is very, very clear. What I said is, what you just understand is the fact that we shifted phase. That's why we can have different forms of the equation. Do well to subscribe to the channel and click the bell notification to get notified whenever I drop a new video. God bless you.